Hello and welcome to another video. This video we will see the modeling of electrical circuits. We had seen modeling of basic electrical circuit. Here we will see a little more complicated electrical circuits. Before beginning, I'd like to mention about the state of a system. The states of a system are the variables that gives us information about the present situation of a circuit. Normally in an electrical circuit, we use VC, voltage across the capacitor, and IL, voltage, the current through the inductor, as the state variables. So the voltage across the capacitor and the current through the inductor, flowing through the inductor, will give you the information about the current situation of the circuit. So that is why those are called the states of the network. And these are general formulas. The current through the capacitor is equal to the capacitance value C into dVc by dt, derivative of the voltage across the capacitor. And VL is the voltage across the inductor, that is equal to the inductance value L and multiplied with derivative of dIL by dt. So here in this circuit, we have a series as well as parallel combination. So we will be using both Kirchhoff's current law and Kirchhoff's voltage law to model this network. Here V of t is the input and the output is the capacitor voltage Vc of t. So by Kirchhoff's current law, we can write L equal to IC plus IR. The current that is entering, that is flowing through the inductor, that splits at this point and it flows through the resistor. One part flows through the resistor and another part through the capacitor. So IL is equal to IC plus IR. And by Kirchhoff's voltage law, we can write V equal to VL plus VR. So in this closed loop, in the first loop, we have the input voltage V of t that will be dropped across the inductor. So VL plus the voltage that is dropped across the resistor, VR. Now the aim is to represent these equations, use these equations and represent and write in terms of the state variables. In this network, we notice that the voltage across the resistor and the voltage across the capacitor are the same because they are kept in parallel. So the voltages which are in parallel are the same. So this equation can also be written as VL plus VC. Now our aim is to express IC and VL as the linear combinations of state variable and the input voltage. That is how we model the electrical network. So from equation 1, from Kirchhoff's current law, we have IL is equal to IC plus IR. I'm taking IL to the left, that is equal to I minus IC plus IL. So IC is nothing but R by R. So minus IR is equal to VR by R. And that is equal to minus VC by R. Since VR and VC, the voltages which are kept in parallel are equal. So minus 1 by R VC plus IL. So this is equation number 3. And we, from the Kirchhoff's voltage law, that is equation number 2, we get VL is equal to minus VC plus V. So we substitute this equation number 3 and 4 in the first two equations. Here I have named it as equation number 5 and 6. So the left side of both these equations are same, IC and VL. So we substitute the right side of both, we equate right side of both the equations and we come up with the equation C dVc by dt is equal to minus 1 by R VR plus IL and L dIL by dt is equal to minus Vc plus V. I'm taking the C to the other side as well as the L to the other side. So our equation becomes dVc by dt is equal to 1 by C minus 1 by R Vc plus IL as well as dIL by dt equal to 1 by L minus Vc plus V. So the final equation will be dVc by dt is equal to minus 1 by RC Vc plus 1 by C IL and dIL by dt equal to minus 1 by C Vc plus 1 by L V. So this two equations will represent the model of this electrical network. We have two equations since we have energy storing elements in the network, the inductor as well as the capacitor. So the number of energy storing elements in a network is equal to the number of equations that you obtain. That's nothing but the order of the system. Here the order of the system is 2 since we have two energy storing elements. These equations can also be represented as in matrix form. In the above equation, the derivatives can be represented with a dot at the top. So on the left side, the matrix vector, we have VC dot and IL dot. So on the right side, we have the matrix minus 1 by RC, 1 by C, minus 1 by L, 0. VC and IL are the state variables, and V of t is the input. So in the first equation, there is no presence of input, so it is 0. And in second equation, we have a multiplication factor of 1 by L. And VC is equal to a vector 1, 0 multiplied with VC and IL. Since VC is, as I mentioned at the beginning of the problem, VC is the output. So this is the output matrix. Now we will see another example, an example with two capacitor and an inductor. So even before beginning of the problem, we can mention the order of the system. Since there are three energy storing elements, we will have the order of the system as 3. Always the current through the inductor and the voltage across the capacitor are the state variables. So here we have three state variables, the current through the inductor IL and the voltage across the capacitor 1, so VC1, and the voltage across the capacitor 2, VC2. So here three state variables. So we will begin with writing the derivative relations. C1 dVC1 by dt is equal to IC1, L dIL by dt equal to VL, C2 dVC2 by dt equal to IC2. Now the second step is to write the balance equation. Using the Kirchhoff's current law and the Kirchhoff's voltage law, we will write the balance equations. So by Kirchhoff's current law, we get IC1 is equal to IL plus IR. So at this point, the current through the capacitor C1, IC1, split as the current through the inductor and the current through the resistor. So I plus IR. So IR is also equal to VR by R. Now VR is equal to VL minus VC. So the voltage that is dropped across the resistor will be equal to the voltage across the inductor minus voltage across the capacitor C2. Also the voltage across the inductor VL in terms of the input and the voltage across capacitor C1 will be equal to minus VC1 plus VI. So ultimately after substitution we get IC1 is equal to IL plus 1 by R minus VC1 plus VI minus VC2. Let this be equation number 4. Now by Kirchhoff's voltage law, we have the voltage across the inductor VL is equal to minus VC1 plus VI. Now again by Kirchhoff's current law, the current through the capacitor C2, IC2 is equal to current through the resistor IL, that is equal to, since both are kept in series, the current will be the same. That is equal to 1 by R VL minus VC2. Now VL can again be written as minus VC1 plus VI. So ultimately the equation becomes IC2 is equal to 1 by R multiplied by minus VC1 plus VI minus VC2. Let this be equation number 6. Now from equation 4, 5 and 6 we have these three equations. We need to express IC1, IC2 and VL as linear combination of state variables VC1, IL and VC2. So we have expressed it in terms of linear combination of the state variables. Now we replace the right hand side of the equation 1, 2 and 3 by using the equation 5, 6 and 4. Taking the capacitance value C1 to the other side, L to the other side and C2 to the other side, we end up with the equation dVC1 by dt is equal to minus 1 by RC1 VC1 plus 1 by CIL minus 1 by RC1 C2 plus 1 by RC1 VI. And DIL by dt is equal to minus 1 by L VC1 plus 1 by L VI dVc2 by dt is equal to 1 by RC2 Vc1 minus 1 by RC2 Vc2 plus 1 by RC2 Vi. This can be written as in matrix vector form. So this is a matrix vector form. Vc1 dot IL dot Vc2 dot on the left side, and on the right side we have the state matrix as minus 1 by RC1, 1 by C1, minus 1 by RC1, minus 1 by 0 and 0, minus 1 by RC2, 0, minus 1 by RC2, multiplied to Vc1, IL and Vc2. These are the state variables, plus 0, 1, 0, Vi, which is the input. Vi is the input. If we consider Vc2 as the output, then the output matrix will be 0, 0, 1 multiplied to Vc1, IL and Vc2. Vc2 is the output variable. So this is how we model electrical circuits. So we will see more examples in later videos. Thank you.